Okay, so it's the last part for the single variable function. We know that it's our second derivative test. Second derivative test for single variable function, and the result is that if its first derivative equals 0, if its first derivative equals 0, then for its second derivative, if second derivative is positive, then it's concave upward. So it's this form. So it's local minima, local minima. And if this one, second derivative is less than 0, then it's concave downward. So it's of the form concave downward. So it becomes local maxima. Local, in this case, it's local maxima. Local maxima. But it's in the, so for this case, we also have the corresponding result for a function which contains two variables, g equals f of x, y. So it's the last one result. Yeah, it has the corresponding result, and it's the last one. So, and it's the most important result in one of the most important result in this section. Actually, it's very important result in this section. This one, second derivative test. So, for second derivative test, now we have two variables. And the assumption, first of all, the assumption is, when you consider all the second derivative test, all the second derivative, we have four kinds of second derivative: fxx, fxy, fyx, fyy. And this one means that we differentiate x firstly. And after that we differentiate y. And this one means that we differentiate y firstly, and after that differentiate x. Okay, and the assumption is that these four second derivatives are continuous near a point AB, and the point AB is in its domain. And its domain, of course, is domain in R2 space. AB is a point in R2 space. And now, the assumption, originally if it's a single variable function, then originally when we consider maxima, minima, we will focus on critical number. But critical number, there are two cases. One is that derivative is 0. Another one is that its derivative does not exist. But for the second derivative test, we focus on the assumption. This assumption, not just critical number. It should have this assumption: f prime c equals 0. So it's not this form. It's not this form. Yeah. Okay. So and under the assumption we have these two results. This statement. And now for the function which contains two variable case, then for this one, first derivative becomes this one. Okay, this one. And as we know, for the critical point of the function f, there are two cases. One is this one. Another one is one of fx or fy does not exist. And for second derivative test, we also should have the assumption. Okay, so it's the first assumption. Fx, consider partial derivative by x and partial derivative by y. Both of them are 0. At the point AB. Later I will give you the example. At the point AB, both of them are 0. Then we consider it's like the determinant. Okay, and we plug in the value AB, the point AB, and for this one, first entry, consider fx. F is second derivative by x, and the second derivative by y, and here is xy, here is yx. And here there is one thing I should remind you. If you are not sure this one is over here or this one, if you are not sure to put fxy here or put fxy here, then it's fine, because if they are continuous. For we have one result before. We have one result probably is in section 11.3. We have this result. If they are continuous, if these two functions are continuous, then what do we have? We must have this result: fxy ab equals fyx ab. Fyx ab. Actually, we have this result. So indeed, this one is always equals to this one. In this assumption, they are always the same. They are always the same. So it doesn't matter to put fxy here or here. That's fine. That's fine. Actually, they are the same. Actually, they are the same. And so actually, it's determinant equals fx as ab times fyy ab subtract fxy ab. It's square. It's square. It's determinant is this one. It's determinant is this one. Okay, it's determinant is this one. And for this determinant, yeah, we have some result. This one we should discuss. Here we consider here for single variable function. When we consider second derivative test, of course we will focus on second derivative. But second derivative here we just have one variable. So once we apply in the value c, we just have one case. For the second derivative is positive or negative. The positive then is local minima. Negative then is local maxima, right? And now we have four kinds of second derivative. So now we should consider determinant. We consider their determinant. So it's equal to this one. And then consider the value. Once we apply in the point AB, consider the value. If the determinant is positive, if its determinant is positive, we have two cases. Positive. Then we should consider f sub xx. F is second partial derivative. And the second partial derivative. If the second partial derivative by x is positive, then it's like this one. Second derivative is positive, then it's like this one. It's concave upward, so it also have the local minima. So here is the local minima. The first part is still local minima. Like this one. And then if the second derivative is less than 0, it's something like this one less than 0, so it's concave downward, so it's local maxima. But they should have the assumption. Under the assumption, determinant D is positive. Here D means DAB, applying the number A, applying the value AB. Here D means the DAB. Okay? But if its determinant DAB is less than 0, then for the point, for this one, FAB is not local. In this case, it's not local maxima and not local minima. In this case, it's not local maxima and it's not local minima. And then in this case, it's also important in this case, because in this case we also have a name for the point AB. For the point AB, we also have a name. In this case, we also have a name. In this case, it's called saddle point. It's called saddle point. In this case, if its determinant is non-zero, so if its determinant is less than 0, then it's, in this case, the point AB is called local, is called saddle point. Saddle point of F. It's called saddle point of F. This one. Saddle point of F. Saddle point of F. And if determinant is 0, then we could not say anything. So no information, no information. Okay, okay, and for okay, so for here for the saddle point, I could give you an example to tell you it's graph by the graph to tell you the example. To give you one example, here for the saddle point, it's something like this one. We could graph it. Actually, you also could check in our textbook. You also could check the graph or the example. It's like a graph. It's like a graph. Here is the x-axis in this point. Here is the x-axis. Here is the y-axis. And here is the z-axis. And for this point, you could see that in one direction, in this direction, in one direction is the maxima. In one direction, but in this direction is the minima. So locally near the point, this point, we could not say it's a local maxima or local minima. Just in one direction, in this direction, in the direction y-axis, it's local minima. It's local minima. But in the direction x-axis, it's local maxima. It's local maxima. Okay, so that's what we say. So near the point 0, 0, near the point it's not local maxima and not local minima. Yeah, and probably and actually in that case it will happen. I mean it's determined in non-zero. It's determined in non-zero. Yeah, you could find for this one you could see it's a let me see. It's one of the examples in your textbook. Okay. Anyway, so now let's practice some example. Let me see. Probably it's I could check it again, but probably it's in your textbook is g equals y squared subtract x squared in page 7. In page this one. Yeah, you could check it. We could check it again. Okay. The graph of f at a point has a shape. In this case, it's called saddle point of f. And its definition. Saddle point of f and its definition. You could say its definition is that it's the graph of f. And the point AB has a shape of a saddle. This one has a shape of a saddle. Okay. Okay, so now let's see. Yeah, f of sy equals y squared subtract x squared. Oh yeah. So this one. Okay, so actually we could change it now. Probably for this function is this one. We could change in page this one. It's the example. So and actually we could change it. Its determinant now. So let me, yeah. So it's called saddle point in this point, and now we could check it. It satisfies this one. So now we check it. It's the value in this one. The graph of f at this point AB, it has the shape of a saddle, something like this one. Something like this one. And the example is this one. So now let me check its determinant. Let me check its determinant. So if we want to check its determinant, we should consider its partial derivative. So first of all, we consider f sub x. So f of xy, now f of xy is y squared subtract x squared. So now first of all, we consider f sub x. Its partial derivative by x. So it's equal to, y is a constant, so it's negative 2x. And fy becomes, now it's constant, so it's 2y, this one. And f sub xx is equal to negative 2. And f sub y is equal to 2. And fxy, now its derivative is constant. If we consider the derivative by, consider its derivative by y, then it's 0. And this one, consider its derivative by x, it's also 0. It's also 0. This one. So what's the, so as we say, if you want to use the second derivative test, first of all, you should consider the case. Partial derivative equals 0, and its partial derivative also equals 0, just in this case. So in this case, you will see x equals y equals 0. So just consider this point 0, 0. We just could consider, if you want to use second derivative test, we just can consider this one. We just have this assumption. This one, for its assumption, we just have this point. Okay? And for this point, 0, 0, we consider its determinant, d0, 0. And the first term is second derivative by in x, and the second derivative in y, and all of them are this one, 0, 0. So its determinant equals negative 2 times 2. It's equal to negative 4. It's less than 0. Indeed, it's less than 0. So indeed, in this case, it's graph is this one, and indeed 0, 0, it doesn't have local maxima and local minima at this point, right? As we say, in the direction x-axis, it's local maxima, right? In the direction x-axis, it's local maxima. I mean, just in the direction x-axis, it's local maxima. But if we consider the direction in y-axis, it's local minima. So when we say local maxima at this point f0, 0, you should consider it's every point near the point 0, 0. So we could not have this case. So indeed, it doesn't have any. So indeed, in this point 0, 0, it's not local maxima and not local minima. Okay, and we call it saddle point. So 0, 0, we call it saddle point. It has the shape. It has this form. 0, 0, we call it saddle point. It's the saddle point of f for this example. Okay, yeah. Okay, so now I give you some example, another example to practice. Now I give you another example to practice. Yeah, here we could. So for this section, I will give you 3 examples, then we finish this one. And the 2 examples are about the second derivative test, and another one is about the absolute maxima, absolute minima. Yeah. Anyway, so let's see the examples we will consider. So we consider example 1. Find a local maxima and the local minima and saddle point saddle points of f. Saddle points of f. And we can see the two functions. First one is fxy equals x to the power of 4 plus y to the power of 4. Subtract 4xy plus 1. And the second one is fxy equals x times s cubed plus 12xy plus y to the power of q. Yeah, and the second one we find the absolute. Yeah, as I think. Let me see. Anyway, let's find. Yeah, find the absolute for this one. Absolute maxima, the minima of the function fxy equals x squared subtract 2xy plus 2y plus 2y d is the same xy. S is between 0 and 3, y is between 0 and 2. Okay, we can see this equation, these questions. Okay, and here, now let's see the first one. Okay, so now we use we could use the second degree test. So second degree test, we should have the determinant, and determinant is positive. Then we have two cases. Determinant in this case is something like second degree is positive, then it's local. Second degree is probably concave upward, so it's local minima. And if second partial derivative is less than 0, then it's like concave downward, so it's local maxima. But it's under the assumption. And of course, we still have assumption is fxy equals fyx ab equals 0 under the assumption. Anyway, so for this kind of question, as we say in chapter 11, almost each question, first of all, you should consider its partial derivative. So first one, you should consider its partial derivative. S sub x. So consider its derivative by x, then it becomes, here is 4x cubed, and the y is constant, so it's 0, and this time 4y is constant, keeping x is derivative is 1, so it's subtract 4y, and the y is constant, it's derivative 0, this one, and f sub y is constant is derivative 0, and this time is 4y cubed, and here y is derivative 1, multiplied by negative 4x is constant, so multiply negative 4x, subtract 4x. Y is constant, it's derivative 0, so this 10. And we should consider the point AB such that this equation holds. Both of them are equal to 0. So you should let it be 0, let it be 0. It should happen. Okay, here I just give the point. Sometimes I just give it. Okay, and for this one, so it's satisfied this equation, it also satisfies this equation. Then for this equation, what can we say? You could see that we move it to right hand side, but both of them have the number 4, so we could cancel it, right? I mean, it's equal to 4y equals 4x cubed, but both of them have the number 4, so we could divide by 4, so you could get this one. And for this one, you also move it to right hand side, so you also get x equals y to the power of 4. So to the power of 3. This one. And For the point xy, the point AB, which we should consider, it should satisfy this equation and also satisfy this equation. So it means that these two equations holds, simultaneously holds, right? So what can we say? Y equals x cubed, but x also equals y cubed. So it's y cubed is cubed. So it's y cubed times y cubed times y cubed. So it's y to the power of 9. So what can we say? Move it to the right hand side, subtract y is equal to 0. And then also we could take out a common number y, and y to the power of 8 subtract 1, subtract 1. So what's the value y? Y equals 0 or y to the power of 8 equals 1, right? But which number to the power of 8 equals 1? Which one? Which number? If it's real number, then it means that y must be positive 1 or negative 1, right? Positive 1 or negative 1. So actually we have two cases, positive 1 or negative 1. Now we also have another case, y equals 0. Okay, and then each one we could write down its corresponding x value. In this case, x equals is this one, 0, in this case. And then in this case, when y equals 1, okay, y equals 1 or negative 1. But when y equals 1, x equals, y is cubed is 1. And when y equals negative 1, x equals negative 1 is cubed is also negative 1. Negative 1. So we have 3 points. 0, 0, 1, 1, negative 1, negative 1. So we have 3 points need to consider. When we consider the second derivative test, we have 3 points need to be considered. Okay. So so before that we should consider let me see. Yeah, we should consider the determinant. But determinant we should consider the second derivative. So second derivative, this term is second derivative by x. Then consider its derivative by x. Then it becomes 4 times 3, 12x squared. And it's constant, so its derivative is 0. This one. And then y, this one, its derivative becomes 12y squared. Okay? And still have xy. So consider its derivative by y, so it's constant, its derivative is 0, negative 4. And this term is derivative. Actually, we don't need to do that because it's polynomial, it must be continuum. And we consider its derivative. So you must have this one. And actually, we could check indeed it's equal to negative 4. So what do we have? We have this one. Dxy is equal to, first term is 12x squared, second term 12y squared. And this one is negative 4, right? So we should consider its determinant. So we consider its determinant is equal to 12x squared times 12y squared, subtract negative 4 is squared. So it becomes 12 times 12 is 14 times x squared times y squared, subtract negative 4 is squared is 16. And finally we take out the 16. So here is equal to 16 times 9. 9x squared y squared subtract 1 is equal to this one. Okay, and for this term, now we just need to check each point. So first one, for example, is 0, 0. So check D 0, 0. So just need to plug in the value, the point 0, 0. So just plug in the point 0, 0. This term is 0, subtract 1. Otherwise, you could plug in this value, it's also fine. Okay, it's also fine. Plug in the 0, 0 value, you could see negative 16. So negative 16 is less than 0. If determinant is less than 0, then it's saddle point. So 0, 0 is saddle point. So 0, 0 is saddle point of f. It's saddle point of f. Second one, the 1, 1. 1, 1. If the 1, 1, then we plug in the point 1, 1, then this part is 144 subtract 16. So it's easy to see it's positive, right? Otherwise, plug in this one is also fine. It's 16 times 9 subtract 1. It's 8. So of course it's positive. It's easy to see it's positive. So determine positive, then we should check fxx. This 10. But fxx, you will see, it's always, this 10 is this one. But it's square, and it's positive number, so of course it's always positive if s is non-zero, right? So actually, you see it's equal to 12. So of course it's positive. Then what can we say? It's equal to 12, so it's positive, then what can we say? So second determinant is positive, second derivative is positive, so it's something like of the form. Second derivative is positive, so it's something like of the form. I mean concave upward, so it has the local minimum. So f of 1, 1 has the local minimum. But you should write down its local maximum or local minimum. So find a value. So you should find the value. So you should plug in the value, the 0.11. You should plug in the 0.11. So it's 1 plus 1 subtract 4 times 1 times 1. So it's 4 plus 1. So the number, the value is -1. And as we say, it's concave upward, so it's local minimum. This value is local minimum. And the last one, the -1. And it's also have the same result, right? It's also equal to 16 times 9 times it's square, so it's also equal to this case. 9 subtract 1, so it's 8. So it's positive. And double, and its second derivative by x is also equal to the same. It's the same. It's also equal to 12, and it's positive. So it still have local minimum. Since it also have the form, you could view it this way. It's concave upward, so it has local minimum. But you should write down the value. Its value. So plug in the value -1, and again you get the same value, right? To the power of 4 subtract 4 times -1 times -1. So it's still equal to 1 plus 1 subtract 4 plus 1. So it's still equal to -1, and it's still local minimum. Okay, it's still local minimum. Yeah, so it's the first question. So you should consider this equation should hold, these two equations should hold simultaneously. And to figure out all the points, 0, 0, 1, 1, -1, -1, and apply and consider its determinant, and consider all the, and discuss all of them. Yeah, discuss all of them. Okay. Yeah, I think we could practice one more example, and for exercise 2 we could check it next time. But for this one we could do it again because it has a similar. It's also just practice one more example. We could practice one more example. Yeah. So second one. This one. So first of all, we should consider is partial derivative. So partial derivative equals, it's partial derivative by x, so it's 8 times 3, so it's 12x squared, plus y is constant, so 12y keep it. X is derivative 1, so plus 12y. Y is constant when we consider derivative by x, so it's 0. Its derivative is 0, so this 10 is 10. And f sub y it's derivative by partial derivative by y, then it's constant, so its derivative is 0. This one, then it becomes 12x is constant, and so keep it multiplied by its derivative is 1, so it's 12x. And this 10 is derivative 3y squared. 3y squared. And then as we say, we should let it be 0 simultaneously. These two equations should hold. These two equations should hold. And solve these two equations. And for this one, both of them have the common number 12, so we could take out. And then here we still have 2x squared plus y. This one. And here both of them have the 3, the number common number 3, so we could take out. So it's y squared plus 4x. And both of them are 0. This one. This one. Okay. Yeah, so what do we have? This one is equal to 0, so it means that this is equals 0. So move it to left another side. So y equals negative 2x squared. We should solve these two equations. And this one is equal to y squared. This 10 is also equals 0. Since the product equals 0, and it's non-zero number, so we could divide by 3. So it's equal to 0. And it means that y squared equals negative 4x. Negative 4x. And then if we want to solve it, here y equals this guy, and then its square equals this guy. So we could plug in the value y. So it's also equal to negative 2x squared. Negative 2x squared. It's square. It's square. It's square. Yeah, so now solve it is equal to negative 2x squared times negative 2x squared, so it becomes negative 2 times negative 4. S squared times s squared, s to the power of 4. This one. So s to the power 4 times s to the power of 4 equals negative 4x. Yeah, so move it to left hand side to this part, so you will get 4x plus 4x to the power of 4 is equal to 0. I mean this 10 is equal to negative 4x. Negative 4x. So move it to left hand side, you will get this one. And you take out the common number 4x, then you have 1 plus s to the power of 3. S to the power of 3 is equal to 0. Okay, then what can we have? What do we have? S equals 0 or s cubed to the power s cubed is equal to this 10 equals 0 or this 10 equals 0. And this 10 equals 0, it means that s cubed is equal to negative 1. Negative 1. And then in this case, which number is cubed equals negative 1? Which real number? Of course, it should be negative 1 in this case. And then you should write down the point. I mean, when s equals 0, what's the corresponding value y? Just, it should say, xy, it should satisfy these two equations. So when s equals 0, of course y is 0. So it's the point 0, 0 in this case. In this case. In another case, when s equals negative 1, you also should satisfy this one and this equation. So plug in the value negative 1, its square is 1. Y equals negative 2 times 1. So y equals negative 2 times 1. So it's negative 2. It's negative 2. Okay, so this point is negative 1, negative 2. Negative 1, negative 2. Okay, so now we have 2 points need to be considered. We should consider these 2 points. And then we should plug in the determinant. So now you should consider the determinant. But for its determinant, you should consider 4 second derivative. 4 second derivative. So you should consider xx. So for this one, you should consider its partial derivative by x. Okay, so you should put down the number 2. So you will get 24 times 2, 48x. And then when you consider derivative by x, then y is constant. So it's g. This 10 is derivative 0, just this one. And then f sub y. Now it's constant. If you consider derivative, it's derivative by y. So constant is derivative 0. This one is 3 times 2 times y, so it's 6y. 6y. And we still have fxy and fyx. And this 10, when we consider derivative by y, then it's constant. So its derivative is 0, and this 10 is 12. This 10 is 12. Ooh, sorry. This 10 is 12. It's 12. And fyx is also, consider its derivative is also equal to 12 yx. So our determinant xy is equal to fxx, fxy, yx, yy. So it's equal to fxx is 48x here. And then here is 6y. And then it's 12, 12. It's determinant. So it's equal to, it's determinant, so it's 48x times 6y subtract 12 is square. So it becomes, yeah, it's equal to 12 is square is 144. And here is this one. Y subtract 144, and it's actually is equal to, they have the common number 144 times, take out the common number, then 2xy subtract 1, it's this one. Okay, so now, we have 2 points need to consider. So now first one is the case, D0, 0. So first one, D0, 0 is determinant. Just once you plug in the 0, 0, actually you could solve it in this part. So then you could see that it's equal to negative 144. You could see negative 144, so it's negative. Once you know it's negative, it's a saddle point, right? It's a saddle point. It's a saddle point of f. So for the first case we solve it. In the second case, now 0, 0 is negative 1, negative 2. It's negative 1, negative 2. So it becomes negative 1, negative 2. Negative 1, negative 2, it becomes this. Okay, it's 144 times 2 times negative 1, negative 2. So it's 4 subtract 1. So it's 3. So it's positive. So when determining positive, you should check fxx or this 10. So fxx negative 1, negative 2 is equal to 48 times negative 1, so it's negative 48. So it's less than 0. Less than 0, so it's like the second derivative is less than 0, so it's concave upward of the form, something like of the form. So it's local maxima. So f of negative 1, negative 2, we know that it's local concave downward, so it's local maxima. But you should figure out its value. Also, we should figure out its local maxima, local minima. So just plug in the value. So it's 8 times negative 1 to cube, so it's negative 8. So first 10 is negative 8. Second 10 plus 12 times negative 1, negative 2, so it's 12 times 2, so it's 24. Plus y cube, negative 2 is cube, it's subtract 8. So finally it's 8. The solution is 8. For its local maxima. The local maxima is 8. Its local maxima is 8. Let me see. Yeah, local maxima is 8. Okay.